This is the first video in the series about momentum, and we're going to start with the concept of center of mass. This is not a topic we really covered in AP Physics B last year, but basically it flows from the recognition that while we have been treating all objects as point particles so far, that's not actually accurate. Many objects are in fact not point particles. So let's say that you were to throw an oddly shaped, let's say you throw a boomerang through the air. Now when you throw a boomerang, it's going to be rotating in addition to moving through the air, with the result that if you were to track, say, the position of this point, it won't take a parabolic trajectory through the air. Instead, it'll take that shape or something like that. But if you pick, there is one point in the boomerang, about there, that if you track that point, it will actually take a parabolic arc. In other words, that is the only point in the boomerang that will obey Newton's laws, F equals ma. And that point is the center of mass. And what we're going to do once we have the idea of the center of mass is that if you have an extended object or a system of particles, you can treat the motion as the motion of the center of mass, which is what is described by all of Newton's laws, Newton's second law, Newton's third law, kinematics, all that. And then we're also going to treat it as rotation about the center of mass. So the motion of this point right here can be thought of as you have the motion of the center of mass, and then you look at the motion of this point, it moves in circles around the center of mass. Of course, in this video, we're going to learn how to find where the center of mass is. Now, if we have symmetric objects, uniform density, which is most of what we work with, the center of mass is the geometric center of the object. If you have a uniform slab like that, the center of mass will be right in the middle. So that's pretty easy. Now, on the other hand, if you have a system of point masses or a collection of several symmetric objects of uniform density, what you do is you use this formula here. I'll rewrite that. The x component of the center of mass, or the x coordinate, is the sum of mi times xi, which is the x coordinate of each object, divided by the sum of the mass. So let's say that you have three particles. They have mass 1, mass m2, mass m3. And then you set up some coordinate system so that you have x, y, and z. And you say that these 3 points have coordinates x1, y1, z1, x2, y2, z2, x3, y3, z3. Then you would use this same formula applied to x, y, and z. So when there's only 3 particles, it's pretty easy to write out without the sigma notation. So the z center of mass would be m1, z1, plus m2, z2, plus m3, z3, all over the sum of the masses. And the y center of mass is m1, y1, plus m2, y2, plus m3, y3, again, divided by the total mass. And if you've got a system of point particles that doesn't have symmetry that you can use, this is how you have to do it. This is the brute force method. However, most of the time, there's going to be some symmetry you can use. Like in this example, this is problem 7 from your textbook. A nitrogen molecule has 3 hydrogen atoms and a nitrogen atom, and it's kind of a pyramid sort of thing. So you've got the 3 hydrogen atoms that make up the base of the pyramid, and then above the center of that is the nitrogen atom. And we're told, actually I'll make that a little bit bigger. We're told the distance n above the base, I'll call that d, it's this number here. And we're also told that the nitrogen molecule is 13.9 times the mass of each hydrogen. So what I'll do is I'll say that each hydrogen has a mass of 1, and the nitrogen has a mass of 13.9, because it turns out that the units don't matter when you calculate center of mass, as long as you use the same units for all the measurements. And what we need to do is find the center of mass of the molecule. Now, using symmetry, it's pretty easy to tell that the center of mass of this molecule will be somewhere along its central axis. And it will be somewhere below the nitrogen atom. So really, we only need to find the z coordinate of the center of mass. And so that z is what we're going to be looking for. Now, if we say that our origin is located at the nitrogen atom, and positive z is downward, just to make computation a little bit easier. To find the z coordinate of the center of mass, that's going to be the mass of the nitrogen times the z coordinate of the nitrogen plus 3 times the mass of the hydrogen times the z component of the hydrogen. The reason I can say that is because all three hydrogens have exactly the same z coordinate, which is d. And then divide by the total mass, the mass of the nitrogen atom, plus 3 times the mass of the hydrogen. Now to make this easier, Zn is defined to be 0, because that's where we pick the origin to be. And that means that the z center of mass is equal to 3, since the mass of the hydrogen is 1, times d, divided by the total mass of the molecule, which is 16.9. Using the value of d that we're given in the problem, that tells us that the center of mass is 1.8 times 10 to the negative 11 meters below the nitrogen atom. And that is how you do center of mass calculations. Very important that you understand the concept. AP won't ask you to calculate it a whole lot, but you need to understand what it is. Now the last thing for today is the idea of the center of mass velocity. If we look at the location of the center of mass, we'll see that it changes, and that means that we can take its derivative. So to get the velocity of the center of mass, you take the location of the center of mass, you take the derivative. And that means that we can put that summation sign into the integral. Now, the sum of the masses in almost all systems is not in fact changing. So we can take it outside of the derivative. Now the other thing is, this summation is in fact a sum. So the sum of the derivatives is the same as the derivative of the sums. And the masses aren't changing. And the derivative of xi with respect to dt is just the velocity. So there are two ways of calculating the velocity of the center of mass. One, you can get the position of the center of mass as a function of time and take the derivative. Or, if you know the velocities of all the individual particles, you can just calculate it this way, which is usually going to be easier, not always. Now for tomorrow, I'm going to be checking question 5, and next time we'll be talking about momentum, which will be mostly review for you.